So this is a talk about building and testing Docker containers. There's a lot of talk about how containers can speed up the development lifecycle, how they can reduce bugs, reduce integration complexity. So this is based on a project that Luke, Tom and I put together last year for China. So these are all different technologies we've been using in the application layer in the system. I've got Angular, Node.js, some machine learning with R, a bit of Java and Groovy code as well. And obviously the benefit of containers is that for each container that we use, we install the Java runtime in one container, and we don't need to share that with the Node containers. The Node just gets the Node runtime. Same with Angular, you just get, in fact, Angular pushed off to S3, Groovy, etc. And for container, we use Docker. Fig has now become Docker Compose, which is a way of defining an application manifest and saying, I want these containers, these three containers to come up, and I want these guys to connect to each other for these ports. And essentially, it's a YAML interface to what you saw Luke typing on the command line. So it just abstracts away that, makes it a bit easier. And CoreOS was our host, which is an immutable operating system. So you don't get to write to it. You bring the thing up with config file, it'll write some systemd units, and then it's only a Docker host for the rest of the time. And everything you're doing goes to the Docker container. If you want to go and debug something, you go in, you start a container, install your debug tools in there, we've got them already, and then you go and inspect the containers through there. And then got a few different data stores, and got ZeroQ, Redis, and Couchbase. Again, like all these guys are sitting inside containers. ZeroQ obviously at the application layer. And then lots of test frameworks as well, because obviously you can't push this code quickly without having it testable. So, just going back through, these are the sort of things that we actually had in containers. They're all quite self-evident really. And the point of the system was to have everything through continuous integration, continuous deployment. The benefits that gives you is that it forces you to test everything. So you can't just throw stuff at production all the time with continuous deployment if it's not provably correct. Because otherwise you're going to break everything for users and they'll be very unhappy. So in order to do this, we have continuous integration. Everything's divided up into its own repository, but there's no branching. So everyone's always committing to mainline, and a successful build on the build server will semantically tag that with semantic versioning and then deploy it, push it off to the registries Luke was talking about, from where it'll get integration tested with the other containers that it immediately depends upon, and then onwards to production. We've got JSON everywhere, baby simplicity. I wrote a really good quote today. The person that debugs your code has to be twice as smart as the person who wrote it. So if you're the smartest person in the room and you've written the code, no one's ever going to be able to debug it, possibly not even you. And that's applicable to distributed systems more than anything else, because you're already dealing with all sorts of different conditions. Running a Docker gives you de facto distributed system architecture. So instead of having everything in one box and you can talk to each other and you know you've got no network latency, you put it into containers and all of a sudden you've immediately got potential latency between everything. Latency can lead to race conditions, the most difficult thing to debug. So just by starting with simplicity, hopefully everything else follows. JSON everywhere is a communication protocol. Cycle time optimization is the amount of time it takes you to commit a change, have a full suite of tests run, and then get to production at the other end. Obviously, as you add more application code, you end up adding more tests, you end up with more startup time, and the test suite will end up taking longer and longer to run, and eventually you might end up with something that you have to run overnight. That destroys all the basic principles that the system's got on. And partial or whole stack deployable on developers' machines. So as Luke showed you with boot to Docker, you can bring up Docker on SEX. Obviously Linux is native, so that's no problem. Even Windows, like Microsoft, are getting involved now, so you can now run Linux containers on Windows, to some extent. And what this means is that you can run your pre-commit hooks doing your integration tests for the whole system. So you don't have to push something you're not entirely sure about, because you've got everything in containers, you've got transitive dependencies where something over here may depend upon what you're doing. You don't know that until you've run the tests. And the containers that you commit in dev go all the way through from test to production. Okay, so in order to achieve this, we have an npm module which contains all the shared code. So that contains linting rules, it contains IDE configs, task configuration, credentials for registrars, things like that. And what that means is, start a new project, you add this as a Git hook, and it comes down and it sets up your repository for you, commit it back, and you've got all your post-commit hooks done, just bang, in one go. So what this last point means is that anytime you make a change to that registry, that NPM module, because it's a dependency of every other module in the system, then one change triggers a cascading build of everything, starting from there, then its immediate dependencies, the whole system gets tested, and it gets pushed to production. So we start with the base image, which Luke touched upon. Now we actually used Ubuntu for this. Since then, there's a BusyBox-based image called Alpine, which is really small. It comes with all the packages you can want, latest versions. So that's sort of where the new trend for these things are going. When I say trend, that's the smallest size of image that you can get at the moment. So if we were doing this again, then we would start with that. But as you see here, this is very similar to what Luke showed. This is actually what we used in production. So start from Ubuntu, set some environment variables that we use down here, and then just very simple installation, clean up the directories afterwards, and then each of these run commands, even though it contains multiple commands to shell out to, that will still just be one layer on the file system. And because we've removed where we do the apt-get update, we then remove this before the run command is finished, which means that that layer is smaller than it would have been if we'd left that there and then deleted it. In which case you would have had, if you imagine like a changelog, like a diff in Git registry, to have that addition and then you take it away again. So just in order to try and minimise the total size. Install Node.js, install NPM, and then this is the shared stuff I was talking about. Right, so another thing we did with the system was have a task runner which is able to run all the commands, all the possible things you want to run in the system. So equivalent to make, let's say, with make jobs, but we use Gulp because we're a Node shop and we're writing JavaScript. It's really fast, it's really nice. Okay, so this is these are the sort of things that we include. So we're able to set a watch and rebuild the Angular stuff. We're able to set a watch and do a whole set of integration tests, which I'll show you later, involve bringing up containers, injecting data, setting up mocks and stubs and various high-level things. So that's really nice, and it means that we can run 4 different test runners. Like I said, we've got Java code, we've got Angular, Node code, we've got 4 different test runners, and that, it's actually on there, but Gulp test will then shell through, and it won't care because of the way we put this task runner together. It won't care what underlying task runner we're using. Gulp test will run whatever test the container needs to be run. So it's just, again, trying to reduce friction. Even the bash scripts tested, and there's small complexities with OS X versus Linux because of GNU, but not too difficult. And importantly, the build server has no logic. The build server runs Gulp test, which is exactly what the developer runs on their machines. Everything switched out environment variables. Apart from that, it's all exactly the same. So this is an example of a microservice. So this is a node-based app. We're coming from the base image that I showed you earlier. And again, similarly to what Luke showed, we've got the base image, create a directory, set it as our working directory, add in the package JSON, install the application's dependencies, install the application, the certificate, expose the port, and that's it. So we don't have any complexity of installation in here, which means that this is quite quick to build. The npm install is the slowest bit, but if you don't change the package JSON, then all these are cached. And let's say you make a change to this file, do a Gulp test, that will rebuild from this point onwards, because all these layers have already been cached. So again, it's just minimizing development time, cycle time, etc. So yeah, that's just a summary of where we are so far. Now the most important thing here is testing. The importance of pushing tests down to the right layer to reduce the cycle time is the most important thing, because if you start putting system tests, which might need to start 2 services, bring up Phantom.js, click around your application, If you do that to make sure that the service is returning a particular value, well, you've wasted all the time it takes you to bring those services up. You've got to deal with the race conditions, you've got to deal with possible latency. So instead, you should be testing that happens just either at a unit test or maybe at a functional level just on the container. Obviously, this is all a question of pragmatism, but without that focus, then it's easy to get lost. So in terms of testing the container itself, there's a few different strategies that we had to use for testing different types of container, because each container has a different nuance, if you like. Isolate components and never test anything outside of its boundary. Ensure it's correct as early as you can, and make sure that you actually report the correct error. So these are the various components we've got. I'll just, in the interest of time, I'll go over it quickly. So data stores, there's not a lot you can do with a data store, because let's say you're putting Postgres into a container. You want to mount a volume to make sure that the data persists outside the container. You want to make sure that you can authenticate. You want to make sure you've got a certain port open. You want to make sure you've got a certain config, so you don't introduce, say, configuration regression. That's about it. You can't go in and test the Postgres code, because the developers have already shipped you a binary which they've written tests for. So all we do for these are build a container, make sure we can authenticate on a given port, make sure it's got a correct schema if it needs one, and do a very small performance test to make sure we can stick data in and take it back out again. So it's really very thin, and that's done against the compiled container, against the built container. Again, it's very similar for queues. You want to make sure that you can actually pass data in one end and out the other, and there's not a lot more you can do. We had some external code in this project, so we shipped some Java files. Again, all you can do is elicit the behaviour. We weren't given any access to the source code, just the jars. So all that we were able to do was reverse engineer to some extent what it was doing, put some data in, get some data out, run multiple different permutations of that, and then when they shipped this broken version, like 2 weeks later, push back saying, change your behaviour. You can't do this to us. Oh no, we haven't. Here you go, here are the tests. And also, obviously, we were able to give that to them as a Docker container. At that stage, they didn't really know what to do with it, so it wasn't much good. And then microservices, this is just a way of saying we're running no code, basically. But these are the more complex tests. So we're able to build a container and then go into it and run npm test inside the container. So that makes sure we've got the correct environment, and makes sure that what's on the developer's machine when he's developing it, because he doesn't want to have to use the container and build phase every time he's doing this. So you can test on his local machine, but also run the same tests inside. He has his unit tests, we have integration tests inside the container, functional tests to make sure that when you've got two microservices that depend on each other, maybe an address book service as part of a customer registration, then you need to make sure that you haven't changed your API. So these sort of tests are all done, and all those tests are stored in the repository of the thing that you're testing. And there's various other things that you need when running Docker containers, like sidekicks, monitoring, occasional, maybe a job to put a schema on a database, or a job to put authorized keys into SSH users into authorized users. These just ran as individual containers and were the only things that weren't really tested. Just briefly, I'm sure you guys know this sort of thing. Testing rules, more or less. These are what we called functional acceptance. Obviously, different projects have different names for different things. This is generally, excuse me, how we classified things and just had a shared vocabulary through the whole project. These slides are up online, so going through them a bit quickly, but they'll be available. So Fig I mentioned earlier, this has now been called Docker Compose, which is the way that you declare this YAML format, and instead of having to type it all on the command line, you say Docker Compose with this file, and it runs Docker start this container, start the container, link this one together, and it just gives you a nice, easy way of visualizing everything you're doing. So what we did is, for integration tests, we described the relationship between two containers with Fig, bring them up, perform the relevant tests, and take it down again. And that saves us essentially with a lot of bash scripts, so it's declarative. So, yeah, so just skipping over to quickly again, as I say, this is now this is Compose YAML for Docker. It still works with Fig, but it's being deprecated. and we only really switch on these few environment variables. So here's an example of a fig YAML. See, it's the image name. Well, this is the name that fig refers to the image as. So the Docker name, actually. The image name. These are the port mappings that Luke was showing you. These are environment variables that you can pass in to, for example, change logging developments. And these links are a single host way of exposing 2 ports over a bridged adapter without having to go out to the host. So those guys go out to the host. These guys are exposed internally to each other, but you can't access them in exactly the same way. Here's another one, just for example. And this broadly is how we ran these tests. No, it's not. Yeah, so essentially you use Fig like this to bring the service up. You run Fig PS to ensure the services that you expect to be there are there and nothing more. You have these RESTful HTTP endpoints on the services so they can report on their current state, the state of their dependencies, the current Git hash that you've got compiled, that you've got built into the container. And these things seem mundane, but when you're trying to debug something and it's on a remote server and all you've got is curl access, then they become a lot easier than trying to get into the container, go on file system and find out where you've checked your code out, etc. Polyn's preferred sleeping, like any good test suites, and these guys are all just a few sort of ancillary things. I'm not going to do a live demo. Here's one I recorded earlier. So this is what happens when you run got tests on complicated component. You've got unit tests going, these are integration tests. So these are introspecting the code, and at this point we've started the functional tests. So we're using Fig to bring up these containers here. That's Fig PS saying that there's nothing running that we want. These guys have been removed, so they're removed. This is the build process in Docker, and this has now started etcd, which is CoreOS distributed data store essentially. Those, finished. Okay, so the end of here, unfortunately I can't scroll it because it's a GIF, but these guys are testing against the container and etcd as a dependency. So they've been brought up, linked together. The container that we're testing has been queried, data's been put in, it's had to use etcd. So what this has shown us is that we can communicate with etcd, we've got the right data stored in the right places for the application, and then consequently everything's passed. And that suite, doesn't actually say, but that was probably, I guess, less than a minute's worth of tests.
55 seconds?
That's for the functional tests, but because it does, the tests happen in 4 stages, so unit, integration, functional, acceptance. How long the whole thing was, I guess, less than a minute. So after the test has been completed, then we've got various deployment tasks. So the image is tagged, so we get a Jenkins build number, as well as the date, in case Jenkins ever disappears, as well as latest dev, and then we push it to a private registry. We then have a suite of system integration tests, so we've proven the container works in isolation and with its immediate dependencies. We also want to prove that when the system comes up, everything still works. So for example, you can route through from a load balancer through into the cluster, your requests map to the right location, and you get back what you expect. Because of the test pyramid, these are tests right at the top. So these want to be the thinnest layer and as few as possible. And it also has the fringe benefit of testing bits of the system that you can't test. We talked about these earlier, routing, support containers. So non-functional tests, these are load tests, security, making sure that you haven't opened anything you shouldn't have done. And again, these are quite difficult and not covered really in this talk. So yeah, load, stress, resilience, just to make sure that you haven't done anything stupid or introduced regressions. Excuse me. And then finally, we had a deployment bot. Now, Luke was talking about orchestration and running patterns and how you actually link things together. Kubernetes is Google's implementation of how they've been running containers for the last 10 years or so. In the Kubernetes talk, the guy says they spin up 2 billion containers a week. They've been using containers since about 2006. They committed the original C group patches to the kernel. They pioneered the whole usage of these things, and they've picked up some amazing guys who are talking about distributed computing in the 80s and 90s who've come on board and are working on this project. What this does is it abstracts away all the difficulties you have with these host mappings. So you bring up 10 containers on weird ports, and Kubernetes brings up an HA proxy instance which inspects those containers, maps itself internally, and if I've got, say, 5 physical hosts, I get a request come into one of those hosts. If it's not the host with the container that the request requires, Kubernetes will route that request via IP tables through to the correct container. So this is all black magic as far as Docker orchestration is concerned. No one else is doing anything quite like this, and it has penalties and overheads because you're doing something that Google do, and Google have the most complex requirements for these sort of deployments. But if we need something that's going to scale horizontally like that, then Kubernetes is glorious. So Kubernetes was not even alpha when we started this project. So we took some of the things it was doing, like rolling updates, zero downtime, service discovery, and reduced the complexity of them and implemented a subset of its features. But these days, I really recommend if you want to see how Google do things at scale, Kubernetes is a great entry point.
It does the same thing that Fig, but on steroids, not?
Yeah, yeah, like a whole gym's worth of steroids. So this is more for deployments. Logging with Docker is still difficult. There's a few, even though Docker does so many things, there are problems of logging, orchestration, where you save your data to. Ideally, everything should be immutable, and you can throw containers around. You can shoot a host in the head, all the containers disappear, and you fail over perfectly. Obviously, that's practically impossible, but that's the holy grail what everyone's trying to go for with Docker in general. So at the moment, logging is just done standard out. CoreOS captures that and sends it to the host. But if you guys are doing this, then this is just a neat little trick that one of our guys put together, just to take the log stash and forward based on what the output is. It's in there for posterity. Continuous delivery, it's one of my favourite things, so I'll just leave that in there as well. And that is it. I think it's quite late, it's 10:05, so if you guys want to ask anything, I'll be eating and drinking. Feel free